Hi everyone and welcome back to my channel. My name is Emmanuel Odwe. Today we are diving into a fantastic world of computer architecture to demystify the crucial concept. Memory cache mapping techniques. Get ready to unlock the secrets behind what your computer ran so fast. Okay, so let's start with memory cache mapping techniques, optimizing the performance. Explore the fundamental foundation principle and advanced strategy for efficient memory management crucial to unlock a peak utilization performance. So let's start with the cache conundrum and why the memory adhesive are crucial. Modern computer system relies on the tri-memory adhesive to bridge the significant speed gap between the CPU and the main memory. Without efficient caching, CPU could not constantly wait for data. Severally limiting performance. Cache store frequency stored data closer to the processor than dramatic reducing access time to improve over system responsibility. So it's a modern cache conundrum face the modern computer face a cache conundrum because of the significant speed gap between the CPU and the main memory. To solve this, they reply to try the memory and without affecting the cache. The CPU constantly waits for the data. Several limits perform. Cache help to store. So the cache helps to store and storing frequency access data closer to the processor and then dynamically reducing access time to improve our system responsibility. So let's move ahead to cache fundamentals, understanding blocks, stacks, and offsets. So we have the cache fundamentals, understanding blocks, types and concepts. So let's start with cache blocks, the smaller unit of data transferred between the main memory and the cache. Typically, we have the memory. So the cache block we have like 32 or 64. When a bit request, its entire block is loaded. So simply, the smallest unit of data transfer between the memory and the cache. When the CPU requests a bit, the entire block. When the CPU requests for a bit, the entire block contains that bit load into the cache. Okay, so let's move on to tag. A portion of the memory address used to identify which block from main memory is currently stored in a particular cache location ensures the correct data is retrieved. So the tag is a portion memory address that identifies which block, so it identifies which specific block from the main memory is currently stored in a specific cache location. The tag ensures the correct data is retrieved. It makes sure that the correct data is retrieved. The offset, the part of the memory address that specifies that exact bit within the cache block. It determines the bits positions once the block is found. So the offset of the memory address specifies the exact bit within the cache block once the block is found. So let's move on to direct mapping cache limited. So this is direct mapping. Cache mapping techniques. Now let's explore three main ways data can be organized in cache. So the first one is direct mapping cache. So the direct mapping cache. In a direct mapping cache, each block from main memory has one specific location. So each block from a main memory has one specific location. It can be placed in the cache determined by a simple modulo operation on its address. This design is straightforward to implement and offers fast lookups. So in simple so in these simple techniques, each main block has its own specific location it can be placed in a cache. It's fast and easy to implement but can lead to conflict misses when two frequency use fight blocks fight for the same spot, causing performance to be degraded. However, it simply leads to significant drawback conflict miss. Yeah, if frequency access memory block map is the same cache location and they continuously waiting to each other, even if the other cache lines are empty. Let's move on to full full associative cache, which also called maximum flexibility and higher cost. So a full associative cache allows any memory block to be placed in any cache line. It offers the great flexibility and maximize conflict misses. As a block are only written when the cache is completely full. This idea placement strategy results in the lowest possible miss rate for giving the cache size. The trade-off is complex and cost. To find a block, the cache controller must be simultaneously checked every tap in every cache line, acquired complex and power hungry compression hardware. It makes fully associative cache in practice for larger sizes, typically limited their uses to small high performance cache like translation look. So the full associative cache is the most flexible technique allowing any memory block to be placed in any cache line. The minimize conflict misses and the result is the lower possible miss rate. The drawback is that it acquires complex and expensive hardware to check every cache limit simultaneously, making it impractical for larger cache. So let's move on to self-associative cache, a balanced approach. The set associative cache states a practical balance between its simple of directing mapping for flexibility of the full associative. In this design, a cache is divided into sets, and each set contains a fixed number of cache lines. A memory bag can be placed in any of the cache lines within its design set. This approach reduces conflict miss compared to direct mapping as multiple blocks can be mapped at the same set within immediate of each other. It keeps hardware complex manageable compared to a full associative cache as compared only to the need to happen to a specific set to access the entire set commonly. Common frequent frequencies include 2 ways, 4 ways, or 8-way set of cache. Okay, associative cache. So this approach sticks to the balance between each other. So I'm talking about the set associative cache. This approach sticks between the balance of to each other. The cache divided into sets. A memory block can be placed in any cache line within the designed set to reduce conflict versus compared to direct mapping whilst keeping the hardware complex manageable. Common configurations are 2 ways, 4 ways, and 8 ways and all that. So cache writing policy, when the cache writes data, the cache uses two main policies. So anytime the cache writes data, it has two main policies: write stop, write to, and write back. So let's talk about the write to. Data is written simultaneously to the boot cache and main memory. This ensures data consistent but can be slower than to frequent main memory access. Simpler implementation and good system where the data consistently is par- is paramount. It's paramount. Okay, so we are going to the write block. The data is written only to the cache immediately. The main memory is updated only when the modified cache block is used 30 bytes to track the modifier. Higher performance during the memory writing, but more complex data. So the write through, the data is written to both cache and the main memory at the same time. So to both cache in the same memory at the same time. It simplifies and ensures data consistent but can be slower. So the write back data is only written to the cache immediately. The main memory is updated only when its modified check cache block is placed. This offers higher performance but more complex and carries a tax of data loss and power failure. Performance the performance of metrics. So you have the high rate, miss rate, and AMAT. So the high rate performance is 95, the miss rate is 5%. 5%. So the high rate, the percentage of the memory access found in the cache. The hit, hit rate means better performance. So anytime you have the higher hit rate, it means better performance. It means the percentage of accessing not found in the cache. So this simply means the performance or the percentage of the access is not found in the cache. The math simply means average memory access time. The metrics gives us a complex view. The memory performance is calculated. Hold on, this is how it's calculated. This is how it's calculated. So practical application in modern CPU cache architecture. The modern CPU, so we have level 1. I1 cache levels smaller, faster, typically split into instruction and data, usually direct map to two-way setup, associative and a whole lot. So I'm concluding. So there you have it. Understanding these cache mapping techniques is a fundamental to achieving high performance computing. As the technologies advance, the evolution of cache architecture will be continuing in a crucial area of research. Let me know. Thank you very much.